Hey guys, welcome back. We now know how to work with HDFS. It's now time to look at the important concepts and processes that make HDFS function properly. In other words, let's learn about the architecture of HDFS. Take a look at this file system check command, FSCK. When we try an FSCK command on a file or a dataset in HDFS, it gives you the status of the file, whether it's healthy or not, right here. It will also tell you the number of blocks that the file is made of, and not only it will list you the blocks, but will also list you the block locations. That is, the nodes where the blocks are physically stored. For example, this block is replicated 3 times in these 3 nodes. Make sense? Right. So now imagine you're running a 100 node Hadoop cluster and you have thousands of big data sets in your cluster. All your data sets are divided into blocks, and the blocks are spread across the 100 nodes. Now, when you add replication to the equation, each block will be replicated 3 times. Now, HDFS has to manage the block information and where it is stored. Managing all this information becomes very complex pretty quickly. I keep saying that HDFS has a global distributed view of the file system, and it knows how to construct a file from the blocks. But the question is how? Time for some terminologies. The nodes where the blocks are physically stored are known as the data nodes. And they are named so because these nodes hold the actual data for the cluster. Each data node knows the list of blocks it is responsible for. For example, going back to the output of the FSCK command, data node 172.31.45.217 knows that it is responsible for this highlighted block right here. And similarly, other data nodes knows that it is responsible for the blocks that they are trying to manage. Makes sense, right? But data node misses a key information. It does not know that block ABC and block XYZ belong to dataset 1, 2, 3, for instance, right? So also any given data node knows only about the block it is responsible for and does not care to know about the other blocks in other data nodes. Well, this is a problem for us as users, right? Because we don't know anything about the blocks and we quite honestly don't care about the blocks. All we know is the file name, and we should be able to work only with the file name in your Hadoop cluster. So the question here is, if data nodes does not know which block belongs to which file, then who has that key information? This key information is maintained by a node called the NameNode. NameNode keeps track of all the files or datasets in HDFS. For any given file in HDFS, NameNode knows the list of blocks that make up the file, not only the list of blocks, but also the location of the blocks. Now you can understand the importance of the NameNode. Imagine NameNode being down in your Hadoop cluster. There is no way we can look up the files in your Hadoop cluster because we won't be able to figure out the list of blocks that make up the files. And also we won't be able to figure out the block's location. Other than the block locations, NameNode also has the metadata of the files and folders in HDFS. Metadata like the owner, size, replication factor, created and modified date times, etc. Due to the significance of the name node, it is also called the master node, and the data nodes are called the slave nodes. Name node persists all the metadata information about the files and folder in hard disk, except for the block location. So, a very good interview question here. Given the block locations is vital for a functioning HDFS, why name node is not persisting that information? Any guesses? Because data nodes have that information. Remember, each data node knows the list of blocks it is responsible for. What it doesn't know that block X belongs to file ABC. Data nodes and name nodes are in constant communication with each other. So when a name node starts up, the data nodes will try to connect with the name node and broadcast the list of blocks that each data node is responsible for. NameNode will hold the block locations in memory and never persist the information in hard disk. Because in a busy cluster, HDFS is constantly changing with new data files coming into the cluster. If NameNode has to persist every changes to the block by writing the information to a hard disk, it would be a bottleneck. And hence, with performance reasons in mind, the NameNode hold the block locations in memory so that it can give a faster response to the clients. So for this reason, you can imagine NameNode as a powerful node in the cluster in terms of capacity. Now, we know there are two types of nodes in the cluster, NameNode and DataNode. We also understand the importance of NameNode. NameNode failure is clearly not an option, but failures in any computer environment is inevitable, and we need to be prepared for that. So when a name node fails, there are recovery strategies. For example, having a secondary name node, and also you can have different cluster configuration like an active standby setup or HDFS federation, which we'll see in advanced architecture chapter. So now you know that for HDFS to function properly, the data nodes and the name node should be in constant communication. So how does the data nodes know the location of the name node? Hadoop has a set of configuration files. In our cluster, the configuration files are under etc hadoop/conf. First, let's look at core site.xml. So let's open that file. This file has a very important property, fs.defaultfs. In this property, we specify the location of the name node. So the name node for this cluster runs on IP 172.3.1.4.5.2.1.6. There are few other properties in this file for different purposes and may not be HDFS specific. This file is made available to all nodes in the cluster. So any node can look up this property and know the location of the name node. Next important property file is HDFS site.xml. So let's open that file. This file lists all the properties that are specific to HDFS. For example, dfs.namenode.nameDirectory specifies the location in the local file system where NameNode can store its files. Whereas dfs.datanode.dataDirectory specifies the location in the local file system where DataNode can store its files and physical blocks. Next property is the HTTP address of the name node, which is specified by the property dfs.namenode.http address. So simply copy the value of this property, which is this location right here, and put it in your browser. And you can reach the name node and get details about HDFS. There is another property which you don't see here, which is dfs.replication, which specifies the replication factor of the cluster. That is, how many times a block will be replicated in the cluster. The default value for the property is 3. So when you don't see a property in the configuration files, Hadoop substitutes the default value for that property. So in our cluster, the replication factor is 3, since it is the default value. Hadoop is highly configurable, so you can find the list of all available properties in Hadoop's website. And I have included the URL in the lesson notes. As we progress in the course, I'll list all the key properties that you need to know. Next, we have two more important files, master and slaves file. Master's file specifies the name of the nodes where the secondary name node will be started. Slaves file will contain the list of all the data nodes. In our cluster, the slaves file does not have the list of all the data nodes because we started the data node using a script individually on each node. The other property files that you see here are related to other services in the cluster like yarn, etc. Now, if you go to the web URL that we got from the HTTP address, you can find more information about the nodes running in your cluster. You can see the capacity of the cluster. We have 3 live nodes in this cluster and 0 dead nodes, which is good. The location of the name node directory in the local file system right here. You can also list the data nodes too by clicking here. So we have 3 data nodes in our cluster. Under utilities, you can actually browse HDFS and you can also look at the logs. Now you know the configuration details of the cluster. It's time to understand the hardware configuration of the nodes in your Hadoop cluster. The hardware configuration varies from environment to environment and highly dependent on the usage of the cluster. CPU, RAM, and hard disk are the three primary elements that make up a node, right? The numbers listed here are just examples and will vary from cluster to cluster. In this example, both NameNode and DataNode have two quad-core processors each. That's powerful. The important difference between the NameNode and DataNode is the memory and the hard disk. The NameNode is usually high on memory when compared to the DataNode because it holds a lot of data like block locations in memory. Whereas the DataNode is high on hard disk space because it has to store the actual data set. Makes sense, right? Finally, all the nodes must be connected in a high-speed network for efficient processing. In this example, we have listed the network as 10 gigabit Ethernet. Now we have an idea about the hardware configuration. Let's get ourselves familiarized with some jargons. What is a rack and what is a cluster? A rack is a group of nodes connected in a network, and a cluster is a group of racks connected in a network. So all your nodes in the clusters are connected. Next, what is a data center? A data center is a physical location where a cluster is housed. Some years back, data centers used to be dark and ugly, but these days data centers are state of the art. Here is the inside of Facebook's data center located in Oregon. Beautiful, isn't it? And here's the inside of Yahoo's data center. Neat and well organized. And here's the outside of Facebook's data center. We learned a lot in this lesson, so let's summarize. We talked about the functionalities of the name node and the data nodes. We looked at HDFS specific configuration properties and also hardware configuration for both name node and data nodes. Finally, we saw that a cluster is made up of racks, and racks are made up of individual nodes connected in a network. So with that, let's wrap this lesson. See you in the next lesson.